All right, so we have a little bit of housekeeping around minimum cuts before we move on to our next topic. We proved a lemma and a theorem last time, right? The lemma that we proved was that there are at most about 2n to the 2 alpha, alpha times minimum cuts. And we proved that using the randomized contraction algorithm. And based on that, we proved a theorem. If you randomly choose every edge of a graph with probability p, if you have chosen p such that pc is the right mu epsilon delta with the appropriate constants set in there, then the probability that any cut is outside of 1 plus or minus epsilon times its expectation is, actually, let me make this delta b. How do I want to say this? Yeah, let's just write delta equal n to the minus order 1. The probability that any cut is outside 1 plus or minus times its expectation is less than or equal to delta. In other words, not being particular about the constants, PC equals order log n over epsilon gives cuts, log n over epsilon squared gives cuts within 1 plus or minus epsilon with high probability. Yes? So we proved that lemma and theorem last time. And we used that to develop first a sampling algorithm for min cuts, right? If we just find the min cut in G of P, this gives us an epsilon approximation in order m over epsilon to the fourth, m plus n over n over epsilon to the fourth time. And then we had this idea of random partitioning into 1 over p copies of G of P. And this gave us a way to pack 1 minus epsilon trees in order, what was it? I think it was m over epsilon squared time. It may be cubed. Yes? And then this was a Monte Carlo algorithm if we only generated one sample. But if we do the tree packing, then the nearly minimum cut and the nearly optimum packing sort of certify each other, and that gives us the Las Vegas algorithm, right? And then the last thing that we looked at last time was this divide and conquer algorithm, right? Where we divide the graph into two groups. We recurse on each group. And then we use Gabo's algorithm to a maximum packing. Right? Yes? Yes, that's exactly right. The point is that we, in the case above, we sort of had this goal of a particular epsilon, and the theorem tells us what value to set p in order to achieve that epsilon, right? You need to set P equal log n over epsilon squared or so. And that's how many groups you make. Now here, we're making 2 groups, right? 2 groups means P equal a half, right? But we still have this relationship that PC equals log n over epsilon squared that we proved in the theorem, right? But we're using it in the opposite direction now, right? Here we have P equal a half, right? And so what that tells us is that epsilon is equal to, again, I'm going to start ignoring logs, about 1 over the square root of c, right? So what that tells us is that in each of the 2 groups that we construct, right, we expect the minimum cut. The expected size of what was the minimum cut becomes c over 2, right? But now we have an epsilon factor, so it might be as large as c over 2 plus 1 over root c of that, right? So the min cut in g of a half is 1 plus or minus 1 over root c times c over 2, i.e. C over 2 plus or minus order of square root of c. Yes? And so I wrote down this recurrence. I said, what this means is that if we start with a graph that has m edges and min cut c, then when we divide it in 2, we solve 2 graphs that have m over 2 edges and min cut c over 2. And then we have to do augmentations. But in each subproblem, we found c over 2 minus, at most, square root of c trees. So the 2 groups together, when we combine their tree packings, we have c minus order root c trees, right? Which means that we only have to augment by an additional square root of c trees in order to get to the maximum tree packing, right? And Gabo's algorithm does that in linear time per augmentation, or near linear time per augmentation. So it's another cost of m times square root of c. Yes, question? What was that? Oh, thank you. 2, yes. Right? And what I argued was that, well, it's true that you're multiplying this term by 2, you're dividing 2 separate arguments by 2, so essentially you're dividing the size of the problem by 4, right? Because sorry, not quite 4, but the dominant term here has an m times square root of c, so this is next going to become m over 2 times square root of c over 2. And even if you double it, it's not going to get as big as the original term, right? So we're going the next layer is going to have 2 times m over 2 times root c over 2, and then you're going to have 4 times m over 4 times root c over 4, and so on, right? But the dominant term is actually going to be at the top, right? Because you still have this decrease by root 2 at each level. And so this recurrence evaluates to order m square root of c. And then I said, wait a minute, am I doing a valid analysis? And we concluded that the answer was no. How come? Yeah? Exactly, right? So here I went and threw in some expected values, right? And they're not even exact, right? Because we don't actually know what the expected value of the minimum cut is. But worse is that this is actually what's called a probabilistic recurrence, where the arguments that get passed in the recurrence are random values, they're random variables, right? And there's actually a quite nice paper with the natural title of Probabilistic Recurrence Relations. which gives general techniques for dealing with this sort of situation. But I'm not going to teach you the general techniques. I'm just going to show you something. Well, I'll show you a general technique that works for this kind of recurrence. It's not as general as what's proven in that paper. The idea for a careful proof is to unroll the recurrence. So we have a recurrence that is creating two subproblems at each level. Now, if we look at a subproblem at some depth d, okay. Well, first of all, how many subproblems are there? There's 2 to the d subproblems. Right? What can I say? What does each of these subproblems look like? Right? It's a set of edges. How can I describe that set of edges that lands in this subproblem? Yeah? Correct. Each node partitions its edges between its 2 children. Now, if I apply that argument inductively, what can I say about level D? Yeah? Yeah, let's be careful because it's probability, right? So they are disjoint, which means they're not independent of each other, right? In the probabilistic sense, but they are disjoint, right? Is that all we can say? Yeah? Yes, it is a partition of the edges, right? It is a disjoint, it is a partition of the edges, of these M edges, into these 2 to the D subproblems. And what can we say about the partition? Yes? Exactly, right? At each step, we are randomly assigning an edge to left or right. And then we assign it randomly left or right to the next child, and so on. So basically, each edge is randomly percolating down the tree, and it is equally likely to land in any one of the nodes at a given level. So what does that make a particular, what does a node at this level look like? If each edge is equally likely to land in that node as in any other node, right? What can we say about the graph here? Yes? Exactly, right? The graph is g of p with p equal 2 to the minus d, right? So what do we know about g of p when p is equal to 2 to the minus d? Yeah? Exactly. We have a theorem about the divergence of cuts for a given value of PC, right? So here we have PC equals 2 to the minus d times c, right? And so we go back and look at our theorem, which says that whatchamacallit, it's like we did when we knew that p was equal to a half, we deduced an epsilon of 1 over square root of c, right? We do the same thing over here, right? If we write this as mu sub as log n over epsilon squared, right? And now we solve for epsilon, right? We get epsilon equals 1 over root PC, right? Which is going to be 2 to the d over 2 over root c, or let me write it as square root of 2 to the d over c at depth d. So as we go deeper, we get a broader range of possible cut values, but it is still bounded in this way that sort of grows exponentially. Sorry, I'm not using the board ideally, but let me stay on this board for a moment. Epsilon at depth d is equal to square root of, or theta of square root of 2 to the d over c. What is the expected, and I'm going to put this in quotes, min cut at depth d? Well, we just said p is 2 to the minus d, so it's going to be c over 2 to the d, right? Which means that with high probability, the cut at depth d is going to be in the range of c over 2 to the d times 1 plus or minus the square root of 2 to the d over c, right? Which, just as I did for the first level, I can write as c over 2 to the d plus or minus, well, I have a 1 over root c and an extra 2 to the d term at the bottom. Yes? Oh, thank you. Thank you. Yeah. Good. So this is how far in absolute terms we can be from our expectation, right? But this now tells us how much work we're going to do at each node of the tree, right? So if we look at a depth d plus 1, right? Sorry, this is depth d minus 1. No, let's call this depth d. Here, our min cut value is at most c over 2 to the d plus square root of c over 2 to the d. Here, at depth d plus 1, our cut value is at least c over 2 to the d plus 1 minus the square root of c over 2 to the d plus 1, right? So if I think about the work that's going to happen at this node, right, I'm going to start with, well, I have 2 children, each with c over 2 to the d plus 1 minus this many trees. So when I put them together, I'm going to have c over 2 to the d trees minus about this many trees, right? Meanwhile, I know that I only need to pack up to this many trees. Yes? So the difference, the additional packing that I need to do is at most c over 2 to the d plus square root of c over 2 to the d minus twice this, right, which is c over 2 to the d plus, I think I probably have something inverted here, but I don't want to go through and fix the math carefully. Double this. Yeah. Right? And so these terms cancel out, and it tells me that I need to pack only about square root of c over 2 to the d trees that I have to augment from one level to the next. Yes? And this is for a single node, right? So I have to do however many edges there are in this node times this many augmentations, right? But remember that at a particular level, the edges are partitioned. I have to do the same thing at every node, right? I have to do this many augmentations at each node at level D, right? So each edge is involved in this many augmentations, but there's a total of m edges on this level because the edges were partitioned. So the total work is m times this quantity. Did that make sense? A question? No? Yes? That's correct. Well, no, each of them takes linear time in the number of edges at that node, right? So remember that there are about m over 2 to the d edges in each of these nodes. So it's m over 2 to the d times this, but then we do that for 2 to the d leaves, so that turns it back into m, but it's still multiplied by a number which is shrinking with d. Right? So what this is essentially telling you is that the work is shrinking geometrically, level by level. Yes? And this is not playing games with expectations. This is using our theorem about tight concentration of cut values. Okay? And again, the exact numbers aren't, this is not an analysis which is very sensitive to the exact numbers, right? All that we need to show is that the work per level decreases geometrically, and we're done. That shows that the dominant term is the work at the root. Right? A question? Good question. So all of this stuff applies with high probability, right? But, well, two things. First of all, how many nodes are there in this recursion tree? Yeah? Great. So, yeah, I was going to cover this next, but I haven't said when the recursion tree stops. Where does it bottom out, right? And it might be a little worrisome, like, sure, the work per level is decreasing geometrically, but if you have an infinite number of levels, then even if you're only doing a constant amount of work per level, you've got a problem, right? So I do need to argue that this recursion tree stops eventually, right? So how can I assess, sorry, I'll come back to your high probability question after we've got this, right? So how can I assess that the recursion stops? What would be a good criterion for stopping the recursion? Yeah?
Either you could do the graph is small enough that you can push forward, or the graph is small enough that you can instantly know that the answer is like 0 or 1.
Yeah, what would give you an answer of 0 trees? What kind of graph doesn't contain any spanning trees at all? Yeah? Yeah, well, we have, right. So when we can't pack a tree, when there is no spanning tree of the graph, right, then you can't pack any trees. Right? And in particular, how many edges do you need for a spanning tree? You need n edges. So if there are fewer than n edges in the graph, you know the answer is 0, right? Right? Notice that although we talked about the contraction algorithm last time, but here we're not contracting any vertices. We're not contracting edges. We're only sampling edges in this stuff. So we're talking about n vertex graphs everywhere. So as soon as you get down to less than n edges, you know the answer trivially, right? Actually, I'll point out that if you're down to a min cut of 0, you're kind of outside of the range of mu epsilon delta, right? We kind of want log n over epsilon squared min cut. If it's 0, that's too small to be log n over epsilon squared for anything, right? So there's a certain point at which the value of the minimum cut becomes about log n. And at that point, you can't say anything smart about the size of the sample, right? But at that point, you know that the value of the minimum cut is log n. And how fast does Gabo's algorithm go when the minimum cut is log n? Well, it's m log n time, right? So actually, we have to stop at p, or at c times 2 to the minus d equal order log n or so. But then at that point, then Gabo's algorithm takes m over 2 to the d times c over 2 to the d time per node, which means that it's going to be mc over 2 to the d time over all nodes, right? But I said, sorry, I'm being sloppy here, right? This quantity is going to be about log n. That's the value of d where that's going to happen, right? So there's a certain level where the expected value of the minimum cut is about log n, and at that point you'll just give up and use Gabo's algorithm directly, right? But that's at depth log c, right? Which means that you're only going to have 2 to the c recursion nodes. So now we can go back to your high probability, 2 to the log c, which is roughly c recursion nodes. And so now we can go back to your question, right? We're talking about unweighted graphs here, so c is less than or equal to n. So we only have a polynomial number of nodes in the recursion. And we can now apply the sampling theorem to each node of the recursion separately and say with high probability that node works. And then we take a union bound over all of the nodes of the recursion tree. Okay? All right. So now we have properly analyzed this divide and conquer recurrence, and we're done with this algorithm. It has a running time of m times square root of c. So let me wrap this up by talking about sort of later work or the sort of state of the art. It turns out you can do better, at least Monte Carlo. First of all, well, further progress came out of looking more carefully at this notion of tree packing. And it observed two things. First of all, it showed a better bound on the number of alpha min cuts. So it put a floor into this exponent, right? I'd claimed n to the 2 alpha using the contraction algorithm. It turns out that by tree pack if you use tree packing to count, you can get a floor here. So, you know, if you're talking about cuts that are like 4/3 times the optimum, you might think that there are n to the 8/3 of them, but actually there's only n squared of them. Okay. And what this shows is that the cycle is completely tight for everything, right? It's numbers, and n squared min cuts, n cubed cuts of value 3/2 times the minimum, and so forth. Those are all optimum. The way you get this floor is you notice that if you pack a lot of trees, right? We showed that with Gabo's algorithm, you can pack about C trees, but you've made the graph directed, so each edge of the graph becomes a bidirected edge, which means that there are two C edges crossing the minimum cut, C in each direction. But what that tells you is that when you pack C trees, you've got these two C directed edges being divided among the C trees, and that means that a lot of the trees can only have two edges from the minimum cut. And that tells you that, that tells you can find the minimum cut just by looking at cuts that use two edges from a tree. And there's only n squared ways to pick two edges from a tree. And this generalizes up that if you want cuts that are 3/2 of the minimum, you can look at 3 edges per tree, and so forth. And this notion of few edges of a tree crossing the minimum cut, right? So let me write out the main idea. In an optimal packing, many trees only have two edges crossing the min cut. Okay? And this gives you this bound, but it also means that you can find a min cut by finding the smallest cut that only two tree edges cross. And this naturally leads you to an n squared type algorithm. But if you use fancy data structures, if you took advanced algorithms, I talked about link cut trees last year, this actually gives you a way of finding the minimum cut in linear time. By checking, you can effectively check all pairs of tree edges in linear time. So we do at this point have linear time algorithms for min cut, although they are Monte Carlo. And I think that's the end of the story for min cut for now. Although I will start talking next about a related problem. But are there any questions about min cut? Oh, I should say all of this is about undirected graphs. In directed graphs, we know very little. There isn't really a better way to find min cuts than Gabo's algorithm or these flow-based techniques. Contraction doesn't work in a directed graph, and sampling also doesn't work in a directed graph. Actually, I should also mention that there's also been a lot of progress on this notion of sampling from graphs. If you want to look into generalizations of cut sampling, cuts can be thought of as a kind of quadratic form. To compute you take sort of the adjacency matrix, and then you can compute the value of the cut by multiplying on the left and right by vectors that identify a 0, 1 vector that specifies which vertices are on which side of the cut. Okay, so the cut is a very special kind of quadratic form. It's been shown that you can use more sophisticated sampling techniques. I don't think the pure random sampling that I talked about works, but you can use more sophisticated sampling techniques to sample a matrix so as to preserve all quadratic forms to within a factor of 1 plus or minus epsilon. And this has a number of really powerful applications in algorithms that I won't have time to teach. But there's a really rich literature on it. The work actually started here at MIT, somebody named Dan Spielman in the math department, although he has since moved to Yale, so they take the credit. All right, I'm now going to shift to the next topic for today, which is network reliability. And I'm teaching this because we can get a lot of mileage out of the stuff we've already done. It's not going to take a lot of time, and it's a kind of a nice result. The basic question of network reliability that we're going to be looking at is if we do have this graph and edges survive with probability p, what is the probability that that graph stays connected? Okay. So this is a natural model for the kinds of failures that can happen in the world, right? You've got a network of wires, and every once in a while an excavator cuts through one of the wires because they didn't check with the city about where the wires are buried, right? And you as an engineer would like to have some confidence that your network is not going to be disconnected by these unfortunate random events that happen to your network. Okay. And there are many variations on this problem. You might only care about whether a particular source and sink get disconnected from each other if the other nodes are only like there as routing nodes to get information from the source to the sink. Or there might be a broader set of what are called terminals that actually matter. And as you just want to make sure that all the terminals stay connected to each other. Okay. And this is not a problem for analysis because you can't just give an answer that is true for all graphs. It's a problem for computation, right? Here is a graph. Compute for me the probability that this graph stays connected or becomes disconnected under this random edge failure model. Does the problem make sense? Okay. I'm going to write this. So actually, I'm going to look at the disconnection probability, and I'm going to write that as UG of P, the unreliability of graph G sampled at probability P. Now, one thing that's kind of interesting about this, we haven't talked much about approximation algorithms, but this problem is very different depending on whether the reliability is very close to 1 or very close to 0. Approximating 1 does not give you necessarily a good approximation to the other, right? So if the reliability is close to 1, then 1 is a good approximation for the reliability, but 0 is a terrible approximation for the unreliability. Right? The ratio between 1 and the actual reliability is very close to 1, so that's a good approximation. But the ratio between 0 and the actual unreliability is infinite, so that's a very bad approximation. If you took advanced algorithms, you know why we look at ratios as the natural measure of approximation rather than absolute differences, right? If, on the other hand, the reliability is very close to 0, right? So what this is pointing at is that if the graph is reliable, then it's the unreliability that's difficult to approximate. If the graph is unreliable, then it's the reliability that is difficult to approximate. What I'm going to focus on is the case where the graph is pretty reliable, and I think this is generally common in the real world, and look at the unreliability, which is the more difficult quantity to approximate. Okay. Now, the sad thing is that this problem is Sharp-P complete. We've talked about this before, right? Sharp-P is the complexity class that involves counting the number of different solutions to a polynomial time problem. Why is that kind of a natural thing to expect for the reliability problem? Is there a way to sort of frame reliability as sort of a counting problem as opposed to a probability problem? Exactly. So if you think about G of 1/2, each edge is present with probability 50%, then the probability of disconnection is just, it requires counting the number of disconnected subgraphs of this graph, and the probability of connection is counting the number of connected subgraphs of this graph, right? So this sort of relates it to the DNF counting problem that we looked at, right? And it's actually quite related, right? Imagine if we have a fail variable for each edge. Okay. Then the event of disconnection can be written as a sort of Boolean formula over these failure variables, right? What is sort of the most basic thing that could cause the disconnection of the graph? Yeah? Exactly, right? A graph is disconnected if there is a cut with no edges that survived, right? So in fact, I can write the disconnection event as a union over all cuts, right, of an and over all edges in the cut of the event that the edge fails, right? Get this backwards. Sorry, I'm having a brief existential moment here. Give me just a second. I want a DNF. Why am I getting a CNF? No, this is a DNF. Thank you. All right, so this is a DNF formula, right? So do we already have an algorithm for estimating reliability? It's a very big DNF formula, right? It has 2 to the n clauses in it. Right? But aside from that little detail, we have an algorithm for estimating reliability, right? Yes?
Oh, sorry, we counted the number of bits.
But you're thinking along the right lines. Okay, so among all of these cuts in the graph, which of them are the most likely to fail? Min cuts, right? Because a cut fails if all of its edges fail. The more edges that a cut has, the less likely it is for the cut to fail. Did I say it backwards? This is why I paused. It's a DNF. It's an OR of ands, right? A CNF is an and of ORs. But I had the same panicky thought. I thought I might have to go retract one of my papers, but it's okay. This is in fact a DNF. Okay. So, min cuts are most likely to fail. Or more generally, right, small cuts are more likely to fail than large cuts. So could we engage in some wishful thinking maybe? If the small cuts are the likely ones to fail, what might we hope would work as a reliability estimation algorithm? Yeah? Good. So hopefully, right, so we know that each large cut is unlikely to fail. If we could argue that overall large cuts are unlikely to fail and we can ignore them, well, then maybe we can just enumerate the small cuts, make a DNF, and use our DNF counting algorithm to estimate the reliability, right? And that turns out to work. So the idea is that only small cuts matter. So we can enumerate them and then use DNF counting in order to get our answer. Okay. Now we know how to enumerate them, right? We talked about this last time, right? Or sorry, we talked about it implicitly, right? I showed you that the contraction algorithm has a decent probability of finding an alpha minimum cut. So if you just run it enough times, then you'll find all the alpha minimum cuts, right? So we just have to focus on this idea that only small cuts matter. But actually, given the time, why don't we hold that, take a break, and then we'll come back and prove it. Nobody wants a break? I know the proof is really interesting, but it'll still be here in a couple minutes. Hi.
Something like the techniques you said that for the linear Minkut.
Mm-hmm.
Were you referring to Spielman's work?
That's the quadratic form stuff is Spielman's work,
the
yes.
sparsification.
That's right, that's right.
Do you think it would be interesting for a project again?
Oh yeah, that's very interesting work. Yeah, that matrix sparsification stuff is really cool. Okay, let's start doing some proving. So What's the most obvious direct way to argue that the large cuts don't matter? What are our basic tools for combining events and things? Union bound, right? So the question is, can we apply the union bound to evaluate the probability that a large cut fails? Okay. So what do we know? We know that a min cut fails with probability p to the c, right? Actually, notice that I'm inverting the definition of the meaning of P here. P is now the probability that you delete an edge as opposed to the probability that you keep an edge. It's just more natural for this problem. And that means that the unreliability of G is at least P to the C because there's a min cut and it might fail. Right? So the question is, can we use the union bound over large cuts to argue that altogether their failure probability is negligible compared to P to the C? Okay. So if we consider an alpha min cut, its failure probability is P to the alpha C, right? We also know from last time that there are at most n to the 2 alpha min cuts. I'm going to be sloppy about my constants again, right? So if there's only n to the 2 alpha min cuts, all right, in particular, there are at most n to the 2 times alpha plus 1 cuts a value between alpha C and alpha plus 1C. I'm just breaking things up to get different bounds for different values, right? And so each of these 2 to the alpha plus 1 cuts fails with probability at most alpha C, right? Any cut in this range fails with probability less than P to the alpha C. So altogether, the probability that any of these cuts fails is at most n to the 2 times alpha plus 1 times P to the alpha C, right? Which is n squared times n squared P to the C all raised to the alpha power. Yes? So the analysis that I'm doing here is tracing very similar to the analysis we did for deviation for the tight concentration of cut values, right? There we used the Chernoff bound, which had this sort of exponential in alpha term that therefore turned into a geometric sum over all possible values of alpha. Here, instead, it's actually an easier analysis. Instead of having to use the Chernoff bound, we just have directly this exponentially decaying probability that a cut loses all of its edges, right? But the formulas are of the same shape. Okay? So is this good or bad? Well, it kind of depends on this inner quantity, right? If n squared P to the C is less than or equal to, say, n to the minus 6, okay, then if I sum over, right, then if I sum over all possible values of alpha, I get a geometric series, and even its first term is negligible, right? At alpha equals 1, right? Or sorry, at a particular value of alpha, right? So if n squared p to the c is, let's see, what did I write here? Yeah, if n squared p to the c is less than or equal to n to the minus 3, then, no, let me stick with what I wrote up on the board. If n squared p to the c is sufficiently small, or is less than a half, then I have a geometric series which is dominated by the first term. Yes? Now, unfortunately, the first term, if I only use that, I still have this n squared out here. Right? So what I now need to compare are UG of p, which we know is greater than p to the c, versus the bound that we would get if we only consider for cuts a value greater than or equal to alpha c, right? Which is going to be, according to that geometric series, about n squared times n squared p to the c to the alpha. So if this is much smaller than this, then we know that these large cuts do not contribute significantly to the value of the unreliability. Yes? So it is sufficient to have n squared times n squared p to the c to the alpha less than or equal to, say, n to the minus 2 times p to the c. Right? That makes the failure probability of the large cuts negligible compared to our lower bound on the unreliability. Yes? And so if you solve for this, there is a this works for alpha equal some constant. Okay. So essentially what we've proven is that for alpha equal 4 or 5 or 6 or something like that, you don't need to worry about the cuts, which are more than 4 times the minimum. Yes? Question? Good. So this is the worry. We're not quite done, right? But let's finish this line of thinking before we go to that line of thinking, right? So if n squared p to the c is less than the appropriate n to the minus order 1, or n to the minus order 1, then you only need to consider alpha min cuts for alpha equal order 1. So you can enumerate them and use DNF counting. So does everybody buy this conditional argument? Okay. And this number is interesting. Remember, there are possibly n squared min cuts in a cycle. And p to the c is the probability that one of them fails. So the cycle seems to be showing up again in an interesting way. But now it turns out we're not done, right? What if n squared p to the c is greater than n to the minus order 1? Or to put it another way, p to the c is greater than n to the minus order 1. In that case, our summation diverges, and we can't say that the large cuts don't matter. So how can we assess the reliability of a network in this case? Well, remember that p to the c, the probability of a particular minimum cut failing, that's a lower bound on the unreliability, right? So we're looking at a case where the unreliability is larger than 1 over a polynomial. Or to put it in a different language, that will be a good hint, the disconnection event is not rare in this network. So if you have an event that is not rare, what is the most obvious way to estimate its probability? Yeah? Sampling. What does that mean in this case? So this network has a reasonably large probability of disconnecting when you kill edges with probability p. So what should you do? Yeah? Exactly. So generate many G of P samples and use the rate of disconnection as an estimate for UG of P. This is the very first thing that we did with random sampling, is just run the experiment and estimate how and see how often it happens. Right? What is many here? Right? How many do I need to generate in order to get a good estimate? Anybody remember that far back? Yeah. And what is the probability of getting a hit in this problem? What is a hit? A disconnect. Right? It is exactly UG of P. Right? But we're looking at the case where the unreliability is large. So this is n to the order 1 samples. So everything works out very nicely, right? We have either the unreliability is larger than 1 over a polynomial, and we can estimate it using, this is by the way, I can't remember if I used this term, this is just called Monte Carlo sampling, which is just a fancy name for generating a lot of samples and counting how often you get a success. Yes? Correct. Fortunately, I had you do DNF counting with weights on homework, right? So that's taken care of, right? You need to use the general P version of DNF counting in order to solve this problem, right? So yeah, if UG of P is large, i.e. bigger than 1 over a polynomial, then you use this direct Monte Carlo sampling. If UG of P is small, then you can show that large cuts don't matter. You can enumerate the small cuts and use our DNF counting algorithm, which at the end of the day is also doing a kind of sampling. It's just you're doing very different sampling approaches for the two cases. Yes? So if you work the numbers carefully, I think it's about n to the fourth. But yes, this is not a practical solution. This is a polynomial time in theory algorithm. Actually, I take that back. We did computational experiments, and it turns out that in practice it works well because most graphs are not at the extreme of this. Okay, but this is not the best algorithm for this problem. There's been a continuation of work on this reliability question, and I'm going to give you a little taste of that progress now, and you'll take a bigger bite of it in your homework on Wednesday, because I want to show you what I think is a quite lovely analysis based on another coupling argument. I think these coupling arguments are really fun, and there's a nice chance to use one here. I'm going to ask you, what is the least reliable graph? With a particular minimum cut? Which is another way of asking, what is an upper bound on the unreliability, right? So we said that a lower bound on the unreliability was p to the c because the graph has a particular cut of value c, and there's a certain probability that that cut fails. Can we compute an upper bound on the unreliability of a graph? Of any graph? Any guesses? Yeah? So if you take, so that's, I think, is generally called a barbell or a dumbbell graph, right? So if we have this constraint that there is a minimum cut of value c, one thing that you can do is fill in everything else, right? Make two complete graphs. Okay. What is the unreliability of this graph? What's the probability it disconnects? Yeah? Yeah. It's very unlikely that either of the two sides is going to disconnect, and so the only way for this graph to disconnect is to have the min cut fail. So this is, in a sense, the most reliable graph with minimum cut c. Is the least likely to disconnect because it only has that one cut that can fail. But I'm asking the opposite question. Can you have exponentially minimum cuts? No, we proved that's not possible. Yeah? C copies of a tree. So, like a tree packing, right? If you put C trees onto the same set of vertices, you're creating a tree packing, basically, right? And if you line them up properly, you can arrange for the graph to have min cuts. Like, if you do that, if you make C trees, the minimum cut will be at least C, but it might be larger, right? And I don't think this will take you where you want to go because, like, your instinct might be that you just need one edge to fail from each tree. But unless the tree, are you making the trees all identical to each other, parallel edges? Okay, so yes, now you're going, if you make C trees that are all exactly the same shape, right, and you put C parallel edges, and there's nothing wrong with parallel edges in a graph when you're talking about network reliability. So in order for this graph to disconnect, you need one of these bundles of edges all to fail, right? And there are n minus one of these bundles, and each of them is now a minimum cut that fails with probability p to the c. So this has a failure probability of about np to the c, which is a lot bigger than p to the c, right? Can we beat that? Can we make an even less reliable graph? Yeah? Good. So we said that, we've seen that it's the minimum cuts that are the most likely to fail, so let's just make a lot of them. And we can use the same idea as for this tree of bundles, right? You can imagine making a cycle where you put now C over 2 edges between every pair of neighbors, right? This cycle, as we saw before, has n choose 2 minimum cuts, and each of them has a p to the c chance of failure. So this gives you something more like n choose 2 p to the c. It's not exactly that because there's dependence, right? But it's in the especially if p is small, it's in the ballpark of n squared p to the c. And it turns out that that is optimal. The cycle is indeed the least reliable network. I'm going to prove that to you with a coupling argument. Okay. So what I'm going to do is I'm going to couple the contraction process, right? We had this notion of contracting edges in a graph. I'm going to take my graph and the cycle and couple the contraction processes between these two. Now, how am I going to connect this to reliability? Well, we want to generate a copy of we want to generate a G of P where we fail all of the edges of probability P, and then we want to check if it's connected. Right? That's what we're doing for this reliability analysis. Okay. I'm going to do this in a very strange way. So we have m edges to start with. Right? I'm going to decide that how many of them survive and how many of them fail, right? So we have B of MP edges that fail and some other K prime, B of M 1 minus P edges that survive, right? So first so instead of flipping a coin separately for each edge, I'm going to flip a coin for, I'm just going to use the binomial distribution to tell me how many edges survive. And then I'm going to choose that many surviving edges. And see if they connect G. So I'm imagining my construction in a different way, right? Where instead of flipping a coin for each edge, I choose how many edges survive, and then I see if they connect G. And I'm actually going to do that in a specific way. I'm going to choose one edge at a time. And I'm going to contract it. So I'm going to ask how many edges survive, and then I'm going to pick one edge at a time from the graph and contract that edge. How do I decide at the end of that whether I connected the graph or not? Yeah? Exactly, right? G is connected if these contractions shrink G to one vertex. Yes? Yes, so for this analysis, when you contract, you may be creating some loops, right? Edges with both endpoints that are the same. Keep them. You might pick them. And when you contract them, nothing happens. Right? So this is just a weird way of generating a sample. Right? The natural way is to flip coins for each edge independently and test connectivity. Instead, I'm generating a certain target number of edges. I'm randomly contracting that many edges, and I'm checking if I end up with a single vertex or not. Is the design of the experiment clear? Now comes the fun part. I'm going to couple this to the cycle. And I'm going to call the cycle Y because calling it C is going to be too confusing with all the little C's running around. I'm going to imagine this is the C over 2 cycle, right? The one that we designed over there. So I have my graph, which has min cut C. I have my cycle, which has min cut C. I'm going to imagine running this process, right? Pick a number of edges and contract on both graphs at the same time in a connected way to get the outcome that I want. Let me also say a little bit more about this cycle. We know that the cycle has fewer edges than G. Okay? Or no more edges than G. How come? Yeah? Exactly. If the min cut is C, every vertex has degree at least C. The cycle has degree C everywhere, so it is minimal. Okay? So I'm going to add loops to get the same number of edges as G. This is for the coupling. Okay, I want these two graphs to have the same number of edges. Okay. So what is this coupled process? Well, I'm going to pick the number k of edges to contract as b of n comma 1 minus p. It's going to be the same k for both graphs. Okay, they both start with the same number of edges, so they have the same distribution about how many edges are contracted. So remember that what we do in coupling is we design two experiments that both follow the rules, but hiding inside there's a dependence between them. So if you don't look inside, you have two experiments that are following the rules, and you can say what's happening to them. But then you can also say things about the connection between them. Okay? So by starting with the same number of edges and picking according to this binomial distribution, I'm contracting for each of these two graphs the proper number of edges for my sampling experiment. Okay? Now, I am going to pair up the edges of these two graphs for a particular contraction step. Right? This graph has some edges. This graph also has some edges. I'm going to pair up the edges, create a matching between them, so that if depending on what edge I pick in G, I'm going to pick the corresponding edge in the cycle. And I'm going to be very careful about this pairing. Okay? I'm going to pair up the edges in each contraction phase. And I'm going to do this very carefully such that the number of contracted vertices in Y never shrinks below the number of contracted vertices in G. Okay, so I'm running this parallel process. I'm contracting edges of Y. I'm contracting edges of G. I am going to make sure that Y is never smaller than G. It always has at least as many vertices. If I can make this happen, then at the end, Y will still have no fewer vertices than G. Right? If that's true, that means that in particular, if G has more than one vertex, then so does Y. right? But what does it mean for G to have more than one vertex at the end of the contractions? Why did we design this experiment in the first place? Yeah? Exactly. This is saying that if G is disconnected, then so is Y. But if this is true, no matter how I run the experiment, that means that the probability that G is disconnected is at most the probability that Y is disconnected. So I've proven that nothing can have a larger disconnection probability than the cycle. And all I need to do in order to prove that is to show you how to pair up the edges. I'm going to do this sort of in a dependent way, right? As the procedure advances, as contractions happen, there's a next contraction step. I'm going to create a pairing of the edges for that contraction step. Okay? So case one is easy. If Y has more vertices than G, then I can do an arbitrary pairing for a contraction. Okay? Because when I do a contraction, at most, I'm shrinking one pair, I'm decreasing the number of vertices by one, right? So if Y starts with more vertices than G, in the worst case, Y shrinks and G doesn't, but Y only shrinks by one, and so Y cannot end up with less vertices than G. So the only challenging pairing is if Y and G have the same number of vertices. Yes? Yeah? No, the pairing is very dependent on the experiment, right? Because I've done a series of contractions. Now I've got some contracted graphs. Now I think about how to pair the edges between those two contracted graphs. Okay? But what's important is that it doesn't matter how I do the pairing, because if I look at each experiment separately, I'm choosing random edges. Right? I'm only creating a weird dependence between the experiments. Each of the two experiments is still a random contraction of edges. Okay? So, only issue is if Y and G have the same number of vertices. And what do I do in this case? Well, as we saw before, Y has the fewest non-self loops of any graph with min cut C. Right? We said that the cycle has the fewest edges, right? When we were ignoring the self loops, right? It just has, right, because its degree is C everywhere, right? So it has the fewest non-self loops, which means that I can pair every non-self loop of Y to a non-self loop of G. Yes? So if I do this pairing, what can I say about the contraction step? Well, what I can say is that if Y shrinks, right, if I pick a